When we have the problem of a three-wire star-connected system and it's got unbalanced loads on the system, so it's three-wire, there's no neutral in this, and we connect an A-phase load which is purely resistive, 3 amps of current, 2 amps on the B phase. That's a lagging current of 30 degrees, and the C phase back to the start point is 3 amps with a 15 amp leading current. So we've got to do a 3-phase phasor to determine the new start point of the installation. So set your phasor up, draw your 3-phase voltage scale first up. So set up the scale, 1 centimetre here's 230 divided by 8 gives me 28.75. So that VA would be representing 230 volts for the A phase. Of course the B phase lags by 120 degrees down there, and the C phase will be lagging another 120 degrees, all 120 degrees out of phase with each other. So we draw our voltage phasor in as the starting point, 230 volts for the B phase and 230 volts for the C phase. Okay, now we plot the currents on the phasor that we know of. So 3 amps purely resistive in the A phase, at, so it'll be 6 centimetres long based on our scale. We draw in that IA. There's into there, that point. That's IA. Equal to, what is it, 3 amps, purely resistive, so it's in phase. The B phase, 2 amps lagging the B phase by 30 degrees. So we get our protractor around this way and we show 30 degree angle after the B phase. There it is, so 2 amps, which will be 4 centimetres long at that angle. There's our IB equal to 2 amps, and IC is 3 amps leading, so it'll be in this quadrant here that's leading by an angle of 15 degrees before the C phase, a leading current there. So 10-15 degrees leading is at that angle up there, and it was 3 amps in length. Okay, so that's our IC equal to 3 amps leading. So I've got these 3 currents all out of phase, the B and C phase. So I've got to add them up by phasor addition to determine the new start point. What's happened to that? So pick any 2. I'll pick B and C. They look nice and easy to start off, and add them by phasor addition. So the length of IC, come to the tip there of IB, get the length of IB and add it to the tip of IC, and where the 2 arcs intersect, of course, is the resultant for the addition of IB plus IC, which is to that point there. So that's IB plus IC by phasor addition, the resultant. So I've added those 2 together, IB and IC. We've also got to add it now to IA. So again, make a parallelogram up, we'll get the length of the resultant and come over and add it to the tip there, scribe an arc, and then get the length of IA, come over to the tip of the resultant and scribe another arc. And where those 2 arcs intersect at that point, just in there, is the new start point. for the installation. So if we, which is in there, it's not working. So in there is the new star point. Okay, so from that point on, then over back to your origin of the A phase, from your star point over to there is about 10 centimetres long. So at that tip across this way, the black line going in there is now the A phase voltage. So that becomes VA from the tip of 230 to the new star point. Will be the new VB, and from VC to the new star point, just down in there, is the new VC voltage. So we play a scale. The length of that one's 10 centimetres long, so 10 times 28.75, 287. So VA is equal to 287.5 volts now. VB is that one in there. It is 9.4 centimetres long, so 9.4 times 28.75 gives us 270 volts on the B phase, and the VC phase, which is that length in there to the new star point, is 5 centimetres long, so that's 5 times 28.75 is 143 volts. So you can see the effect where you've got an unbalanced load and the star point shifts and the phase voltages become unstable. So the A phase jumps up to 287, B phase 270, and the third phase, VC phase, drops right down to 143.